Hello, this is the introduction to the pool boiling lab. I'm going to go through today the various requirements for the report. But before I get started, I want to talk a little bit about the physical situation we have in the lab. In our lab, in the pool boiling lab, we have a chamber. It's a sealed chamber, and inside the chamber we have a heating element in the bottom that's immersed in a liquid. It's some type of refrigerant. Then above the liquid down here, we have a vapor up here, and then there's a cooling coil in here. Okay. Now we have the chamber is instrumented with a pressure transducer, so we know what the pressure is inside the chamber. There's a thermocouple attached to the heating element, so we know the temperature of the heating element. And then there's a thermometer that's immersed into the fluid that we can read, where we can get the bulk temperature or the temperature of the fluid. We define a term called the excess temperature. The excess temperature, which is called delta TE, is defined as the difference between the surface temperature of our heating element and the bulk temperature. So it'd be the difference between this surface temperature and the bulk temperature. Now what's going to go on in this lab is first we're going to turn the power on just a little bit. So we'll start to get a little bit of heat in here, and we'll turn it up until we, and initially we're going to get convective heat transfer, and as it gets hotter, of course the hot fluid will try to rise to the top, and we'll build up a circulation pattern. As we increase the power, we'll start to get little bubbles forming on the surface of the heating element. At some point, we'll get the power high enough so that the bubbles will they'll enlarge and they will actually detach, and we'll get boiling, and you'll have boiling heat transfer here. And in that regime, we'll have what they call nucleate boiling. Initially, we have free convection boiling, then we move into nucleate boiling. Now, as we turn the power up, eventually we're going to get high enough so that all the liquid around the heating element actually vaporizes. When it vaporizes, there will be a blanket of vapor all the way around the heating element, and at that point the heat transfer goes down because we don't get as good a heat transfer through a vapor, and we reach what's called the critical heat flux. And at the critical heat flux, the temperature will increase rapidly because the only way that we get heat transfer at this point is through conduction or radiation. So the heat transfer goes down and the temperature of the heating element goes up, and at that point we have a burnout, or we have the critical heat flux where the equipment will shut down or it will destroy itself if it's not automatically shut down. Okay, so in your lab report, first of all, we'll just go through the steps of the requirements of the lab report. First, it says write a one-page letter. Okay, here I want you to follow the format that's shown in the document called Letter Format and Frequently Asked Questions. Okay, on the second page of your lab report, you're asked to draw a plot of the wall heat flux versus the excess temperature. Remember, the excess temperature is the wall temperature minus the bulk temperature. And you're going to measure the wall temperature and you're going to measure the bulk temperature. Okay, now if we go over here to this board over here, you'll see I've reproduced figure 10.4 in your book, if you have the 6th edition, and this is a typical boiling curve. Now, this is one that someone else has measured, and over on the vertical axis we have the excess temperature, and then down on the horizontal axis, I'm sorry, I think I have that backwards. We have we have the heat flux on the vertical axis, and we have the excess temperature on the horizontal axis. Okay, so you can see for a typical boiling curve, we start out over here on this side of the curve. As the excess temperature goes up, you see that the heat flux goes up. Over in this region, we're in the free convection boiling. Then we reach this portion of the curve, the steep portion, which is called nucleate boiling. Remember, that's where there are little bubbles forming and rising to the surface, and you can see it goes up. Well, it reaches some maximum heat flux, And then you can see this curve goes down. Well, we're going to talk about this in class. It doesn't actually go back down. But at this point, we have what's called just what we talked about, the critical heat flux. So you're going to be plotting in the lab, you're going to be measuring this portion of the curve. Okay, so you're going to measure the excess temperature and the heat flux and plot this. Now, on this same graph, so we'll only be getting this portion of the curve over here. On this same graph, you're asked to plot the predicted heat flux. All right, in order to get the predicted heat flux, we use what's called Rochnell's equation. That's this equation here. That's equation 10.5 in the 6th edition. Okay, you can look up these terms in your book. And you're going to be asked to do this for two different pressure situations, 3 psi and 11 psi. And remember, these two pressures are gauge pressures. The 3 and the 11 psi are gauge pressures. When you do your calculations, you're going to have to use absolute pressure, so you'll have to add atmospheric pressure to that. This is Rochnell's equation, so you have to go and you have to look up, for example, all these different terms for these temperatures. You plug them in and you plot it. You're going to have to look up either the properties or you may have to calculate them. For example, the density of the vapor depends on pressure, so that's not something that you can look up. You're going to have to calculate that for each temperature. You'll know what the pressure is, and you can use the equation of state to get that. Okay, you have two terms here that you don't know. You have CSF and an N right here. Okay, those terms, well, the N can come from table 10.1 as well as the CSF, but I believe, well, yes, you were asked to plot these and use the CSF that best matches your data. Okay, you're also going to have to do an uncertainty analysis for this equation, and you can see this equation is pretty complicated. In order to take the partial derivative with respect to each one of these terms could be very time consuming, or you can type it into MATLAB and let MATLAB do the partial derivatives for each term for you and copy and paste those into an Excel spreadsheet, then put your values in. Either what, well, no matter what you do, it's going to be time consuming, but you can cut down your time probably by half if you take advantage of MATLAB to do the partial derivatives. Okay, please note that there's an uncertainty associated with every one of these terms. That's even G has an uncertainty to it, the gravitational term. We have to determine what those are. Okay, and I'll leave that up to you to determine how you're going to get the uncertainties. Okay, page 3 of your lab report. It says, using a log-log scale, plot H, meaning the convective heat transfer coefficient, versus the wall heat flux for both the high pressure and low pressure boiling data. All right, in the lab, you're going to collect the heat flux versus delta T. Then you can use that delta T to calculate H, the convective heat transfer, using this equation here. This is Newton's law of cooling right here. So you have H is equal to the wall heat flux divided by the delta TE. So you know what H is. So now you can plot H for each one of these versus Q versus the wall heat flux. Okay, now, once you've done that, then we're going to move over here to page 4. Page 4 says, according to the VDI heat atlas, H is proportional to the wall heat flux to the M power. Okay, we don't know what M is at this point, and we are asked to obtain M from the plot you made on page 3. And we're going to compare that with the value predicted by the VDI heat atlas. Well, the predicted value it's a function of P star, which I'll define in just a second, is equal to 0.9 minus 0.3 times P star to the 0.3. Well, P star is just equal to whatever the pressure is in the chamber divided by the critical pressure. You can look up the critical pressure on the data sheet. It has the properties of the fluid, and the critical pressure is one of those. So it's going to change as the pressure changes, P star changes. All right, now to get M, we have that H is proportional to the wall heat flux to the M power. Okay, well, if it's proportional to the wall heat flux, then we can add a constant of proportionality and make that an equation. And we'll have that H is equal to CQ wall to the M. Okay, so now I've turned it into an equation. Let's go over here. All right, I'm now going to take the logarithm of both sides, and I'll take the log base 10 because we did our plot on log paper. So the log of H is equal to the log of C Q wall to the M power. We still don't know what C is. Using the law of logarithms here, we have the log of H is equal to the log of C plus the log of Q wall to the M power. And again, using the properties of logarithms, we can write that log H is equal to log C plus M times the log of Q wall double prime. Okay, this is the equation of a straight line on log paper. So on regular paper we would have y for a straight line is equal to y is equal to mx plus b. M is the slope, b is the y-intercept. Well, on log paper, log c would be the y-intercept, m would be the slope of the line. So if we find the slope of the line on log paper, then we've determined what m is in our equation. And then we can compare that with the value predicted by the VDI heat atlas. Okay, the next thing we're supposed to do for the lab, this would be page 5, is to plot the critical heat flux versus pressure for the 4 pressures that you're going to measure. You're going to measure the critical heat flux for 4 different pressures. Remember, the critical heat flux is when we get that blanket of vapor around the heating element and the temperature takes off. Well, when we get to that situation in the lab, you'll see the temperature as you increase the power, the temperature will come up very gently, and then all of a sudden you'll reach that critical heat flux and the temperature will just take off like that. So you're going to record whatever that temperature was. And then you're going to plot that critical heat flux for 4 different pressures. You're going to do it at 3, 5, 8, and 10 psig. Okay, once you've done that, on the same graph, you're asked to plot the predicted critical heat flux. The predicted critical heat flux is calculated using what's called Zuber's correlation. Okay, Zuber's correlation is found in Chapter 10. A lot of these values you can look up. Again, the density of the vapor you cannot look up because that depends on the pressure. But to calculate the density of the vapor, we can use the equation of state. We have P over RT. We know what pressure is. We know what temperature is. This is the specific heat constant for the gas. It's not the universal gas constant. So we don't have, R is not given to us, but we can calculate it because we know the universal gas constant and we know the molecular weight of the material, so we can calculate R. And so from that we can get rho V. Remember, when you do your calculation, use the absolute pressure, not the gauge pressure in your calculation. Okay, finally, On page 6, you're going to put your original data sheet. That's pretty self-explanatory, but be neat. Be very neat with your original data sheet. It's not necessary to turn in the data sheet where you wrote your values in during the lab. You can retype those into a spreadsheet if you want to be neat. That's probably a good idea. But we need your original data so we can see what you did. Okay, and then finally, on page 7, you're going to put your sample calculations. Let me remind you, on sample calculations, I want you to show the steps that you followed in a neat, linear, orderly fashion. Put numbers in as well as units and show how the units cancel out. If you just put numbers with no units, it's not going to be right. We can't tell what you did if you don't put the units in. Also, if there are any equations that you use from the book, and there will be, you need to reference those. And I showed you how to do that in class. Last words of wisdom here. I strongly urge you to set up a spreadsheet with all the equations ready to go when you come to the lab. Do all the calculations prior to the lab. You can put some sample data in. You can take some numbers. For example, you can set up some excess temperatures you can take off of that graph that we had on the board earlier, and make sure that everything is correct. Check your values. Do a couple of them by hand to make sure that the equations are right. Have that set up. When you come into the lab, you should be able to do a good job. The lab does take about 3 sets of hands to do, so make sure everybody's there. And it will probably take you the whole period to do it, so give yourself, you might want to come in a little bit early to discuss it, maybe see what the previous group is doing, and you should be ready to go. All right, thank you. Now we will move to the actual apparatus demonstration. This is our pool boiling apparatus. It consists of a chamber that has a refrigerant in it. It has a cylinder at the bottom that is our heating element. The cylinder is instrumented with a thermocouple so that we can measure the surface temperature of the heating element, and that's measured, you can read that on this gauge right here. There's a pressure sensor inside the cylinder, or inside the chamber, and we can measure the pressure right here. This pressure is in gauge pressure. And there's also a thermometer inside the fluid that we use to measure the bulk temperature of the fluid. There is a cooling coil up here that cools the fluid by condensation. We have water that flows through the coil. We control the flow of the water with this rotometer here. Okay. We can read the power that's being applied to heat the cylinder actually indirectly off of these 2 gauges right here. This is a voltmeter here. This is an ammeter down here. So we take the product of these 2. The product of the volts and the amps is the power. Now, in order to read this gauge, normally we would have the switch. When we first start, we'll have the switch in the up position. When the switch is in the up position, we read the lower voltage on the scale. There are 2 scales that you might not be able to see, but this is in your write-up. When the switch is in the up position, we read the lower voltage, and then we read the amps directly. When this goes off scale, when it's no longer far enough for us to read, we can put this switch down here to the lower position, and in that case, we read the volts directly off the upper scale. We multiply the amps by 2 and take that product. I think that'll be a little more obvious when you start operating it yourself. Okay, prior to beginning the experiment, we need to purge any air out of the chamber so that the only vapor that's in the chamber is our performance fluid. Your TA will do this for you. We want to conserve the fluid because we don't have much left. Let your TA do that, and then he'll get you started. Okay, now, in order to operate this equipment when you're ready to start, first you turn on the water with this blue handle, the main water supply over here by the wall. Then you turn the power switch on right here, and we can start by setting the power to about 50 watts. Okay, and we're ready to begin the experiment now. Okay, the first experiment you're going to do is determine the critical heat flux for different pressure chambers. And, okay, so we want to find out when you reach the critical heat flux that we talked about in class at different pressures. So we're going to do this for pressures of 3, 5, 8, and 10 psig. The way we do that is we set the pressure by turning up the power. We'll turn the water all the way off, and we'll turn the power up probably about 50 to 75 watts. Depends. When you get here, you'll pick up power that gets it there. And we want the pressure to go up to 3 psi gauge. It takes a little while for it's hard to get the pressure to come up. It's a lot easier to get it to go down. Okay. So once it gets up to 3 psig, then we can adjust the pressure by adjusting the rate of cooling by adjusting the flow of water. So this is really a three-man experiment. One person will adjust the water in order to maintain the pressure. Okay, once we have that, then we will just slowly increment the power up until we reach the critical power flux. And we'll know that we have that when we can know when the equipment shuts off and when the gauges take off, are no longer able to maintain a certain power. So I'll run it up here, and when we get to the critical, it's a little hard for me to do this by myself. But once you get to the critical power flux, what's going to happen is these gauges will take off just like they did. I don't know if you can see it, but they will go up really fast, and then the equipment will shut down. Okay, we're going to do that same procedure. So you're going to have two people over here, one recording the voltage and one recording the amps, because it's going to go off and on really fast. When it takes off, it's going to take off fast. So one person will be watching the voltage, one person will be watching the amps, one person will be controlling the power, and one person will be controlling the water flow. So record that power for that particular pressure. That will be your critical heat flux. Then you're going to set the power, or I'm sorry, set the pressure to a higher pressure. I believe it's 5. It's the next pressure on your write-up. And then you're going to repeat the experiment. You're going to do that for your 4 different pressures. That will take care of measuring the critical heat flux for your 4 different pressures. Okay, the second experiment you're going to do is to obtain a low pressure boiling curve. Okay, this is what you're trying to do. What you're trying to do here is reproduce the curve in your book under nucleate boiling. You're going to be under that regime of the boiling curve. And so we're going to set the pressure by adjusting the power and the water flow to 3 psig. Okay, then we're going to, when we've done that, then we're going to slowly increment the pressure up, and you can choose the, power up. You can choose the power increments, and we're going to record the temperature. So we'll have a bulk temperature, which should stay fairly constant, and then we'll have a surface temperature that we read off the thermocouple. Okay, the difference between the thermocouple temperature and the bulk temperature is what we call the excess temperature, and then we're going to plot that, this excess temperature versus power. And we'll just keep incrementing the power up until we reach the critical heat flux for 3 psi. Then we'll repeat the experiment for a chamber pressure of 11 psi. So you'll have to let the pressure increase. You can read it up here. It takes a little while. We'll get up to 11 psi. One person over here will maintain the pressure. They will watch the pressure gauge while they're adjusting the water flow. And then one person will just increment the power, and then you will have one person reading the temperature, one person reading the thermocouple, or that same person can read that, and you'll just keep increasing the power again until you reach the critical heat flux. So you'll get two curves, one for 3 psi, one for 11 psi. Okay, once you're done with that, then the experiment is over. I expect it'll probably take you about 45 minutes to do all this. Then just turn the power down. If you have another group coming in, just turn the power down to almost zero, not quite zero. You can leave the water wherever it was. Well, you might as well turn it all off, I guess. Okay. And then come over here and turn the water off at the main water supply. And when you're done, the experiment is complete. I would strongly suggest that you create a spreadsheet that you can enter your data in directly so that you can plot it while you're still here and make sure you did the experiment right. It is very common for students that do not check their data while they're here and plot it to get home and find out that they did the experiment wrong. If you plot your data while you're here, have your uncertainty analysis ready, then you will know that you did it right and you can leave and you'll be just about done with the experiment. And that takes care of the pool boiling experiment. Thank you very much.